Welcome back. The next experiment that we are going to conduct is to determine the refractive index of a glass slab by using a traveling microscope. So, there are different techniques of determining the refractive index of a material. Here we are going to use a variant of compound microscope, which is also called traveling microscope, where the you will be seeing in a little while that simple microscope can move up and down, and using that we are going to determine the refractive index. In fact, this is a very simple experiment because the theory involved is also very simple. All of us know about the concept of real depth and apparent depth. We have all seen that how things appear to be raised if seen from a different medium. So let us first understand what is the relationship between real depth, apparent depth and refractive index of a material. Using this concept, we are going to apply and use the traveling microscope to determine the value of refractive. So let us imagine that there is a glass slab. And suppose I have an object at the bottom of a glass slab. So this is the thickness of the glass slab. Let me call this thickness as small t. So the small t is the real thickness. So if you are looking from the top, the glass slab of thickness t, this point p is at the bottom of the slab. So the real depth is p or real thickness is p. Now if I imagine that a ray, suppose it is traveling from P to refract this way, because this is glass has a larger optical density or greater refractive index than air. So this is optically denser, this is optically rarer. So when light will travel from denser to rarer medium, it will bend away from the normal. So consider this as the angle of incidence and this as the angle of refraction. Okay? Suppose this point is Q. For our discussion, let us assume that the point P is the one that is going to act like an object. This is point Q where it refracts. And suppose refractive index of the material of this glass slab is N. Now, if I have to observe the ray from this point, it will appear to me as if this ray is coming from some point here. Consider a normal drawn like this. So, for this person, for this observer, this refracted ray appears to come from this point. I will call this point as P1. So this is going to act like the observed image. So this from the point from a medium, a rarer medium, this point P appears to be raised to point P. So if I consider this point as S, then SP1 is my apparent depth or apparent thickness. Whereas SP is the real depth or real thickness. So we have to find out a relationship between the real depth SP and apparent depth SP1. So for this, we will be using a little bit of Snell's law and simple geometry with a little bit of approximation. So if you look at the triangle, SPQ triangle, if you look at this triangle SPQ, of course this is a right angle triangle, then if this angle is I, this angle is also I. So if I consider the triangle SPQ, sine of I is perpendicular by hypotenuse, so it is QS divided by QP or PQ. Now if this angle is R, you can see that this angle will be R because these are all corresponding angles, parallel angles. So if I now look at triangle SP1Q, then sine of R, if I consider this triangle, sine of R will be QS by P1. But what is sin I by sin I? We all know Snell's law. So by Snell's law, is sin I by sin R. Of course, you have to be careful. This represents the refractive index of air with respect to glass. So I should write it as GA. So that if you do the math, it is P1Q by PQ. But most of the times we go for the absolute refractive index, where we try to find out the refractive index of the material with respect to air. So NAG is 1 by NGA, which is actually PQ by P1. I'll just invert. Now, here you have to make a small assumption that if your point Q is very close to S, so you are not really observing these angles are small. So in that case, if point point Q is very close to S, so if Q is close to S, that means I am observing normal. Then in that case, P1Q can be, this distance is almost equal to P1S, is approximately to P. And similarly, PQ is almost equal to PS. So now, if you look here, so this will be NAG is, in place of PQ I can write PS, and in place of P1Q I can write P1S. And what is PS or SP1? Is it not the apparent depth? P1S is the apparent depth and PS is the real depth. So it is real depth by apparent. So now we have a very simple formula which relates the refractive index with real thickness and apparent thickness. But how are we going to determine this? So determining the real thickness and apparent thickness with much precision requires a good and more precise device, and that is where this travelling microscope comes in. Travelling microscope is nothing but an improvised version of your compound microscope, which has got two lenses, two coaxial convex lenses, which are placed at the ends of one tube. So the distance between the objective and the eyepiece cannot change, it has to move simultaneously. So as shown in the diagram, you can see that there will be, first we will try to position the microscope without making any point, then we will make a mark, then we will adjust so that the point is focused, so that we can get an idea about the real depth and the apparent depth. And using the proper tabular tabulation, we will be able to get an idea of actual real depth and apparent depth, whose ratio will give us the refractive index, which will be elaborated in detail by ma'am when she demonstrates the experiment. Thank you so much.
Let me start now. We are going to use a travelling microscope to find the refractive index of the material of the glass. First of all, to start with, we will check whether this traveling microscope. The base of this microscope is horizontal or using a spirit level. You will keep the spirit level here and there on the base, and you will check this microscope is horizontal. If not, you have to adjust these screws. These screws at the base to make the base horizontal. Now, here you can find so many screws are there. Here one screw is there to move this microscope from left to right. Here another screw is there to move it forward backward. Here also there is one screw to move it up and down, which we will use actually for this experiment. As we are going to focus the plasma from the slab, only we need this vertical movement. First of all, let me explain what is here. You can see here there are two scales. One is linear scale similar to that of a meter scale, and there is a vernier scale. Actually, this is nothing but a vernier calipers here, which will be used to note the positions of the plasma. This vernier calipers has a least count of 0.001 centimeter, unlike the common vernier calipers which we use in the lab. The vernier calipers which is used in the lab has a least count of 0.01 centimeter. But here the least count is 0.001 centimeter. How to find the least count of this vernier calipers? To do that, first you bring it down so that the zero mark of the vernier scale coincides with the zero mark of the main scale. Now, you will find here 50 divisions are there on the vernier scale, and when you bring it down, you will find 50 vernier scale divisions. 50 vernier scale divisions coincides with 49 main scale divisions. That means that is equivalent to 49 main scale divisions. And on the main scale, 1 centimeter is divided to 20 subdivisions. That means 1 MSD is equivalent to 0.05 centimeter. 50 vernier scale divisions is equivalent to 49 main scale divisions. So what is the value of 1 VSD? 1 VSD is equivalent to 49 by 50, and 1 main scale division, 49 by 50 main scale divisions into 0.05 centimeter. That will be equivalent to 0.049 centimeter. Now, the least count of the vernier calipers is equivalent to 1 main scale division minus 1 vernier scale division. That is 0.05 centimeter minus 0.049 centimeter. That is equivalent to 0.001 centimeter. This is the least count of the vernier calipers, which will be used to take observation. Now, here a crossmark was drawn on the paper, which will be focused using the traveling microscope. This was kept below the lens of the microscope. You have to see through it so that the intersection point of the crossmark just coincides with the intersection point of the cross wave. and the clear image here. Now you will note the position of the cross mark using the traveling microscope. For that, you have to note down here cross mark P. How to note? As it is a vernier calipers here, using vernier calipers formula, main scale reading plus vernier coincidence into least count will give you the position here. Main scale reading, what is main scale reading here? The reading of the main scale, with which zero of the vernier coincides. That is the main scale reading. We will note. Plus vernier coincidence. Vernier coincidence, out of the 50 divisions of the vernier scale, which division of the vernier scale is coinciding with any division of the main scale. If you cannot see, you will use a magnifying glass which is given here. Using a magnifying glass, you will find out of these 50 divisions, which division is exactly coinciding with the main scale division. That is vernier coincidence. And multiplied by least count. Least count already you have found the 0.001 centimeters. Then you got the position of the cross mark. Then, without disturbing it, you will put the glass slab on the cross mark. Put the glass slab on the cross mark. What happens? Because of reflection through the glass slab, the cross mark appears to be raised. So, without disturbing this collimator screw, only you raise it upward and focus so that again the cross mark can be focused. Adjust and focus so that you can see the cross mark as you were seeing earlier. Done. Take the position now. Take the position. Similarly, you will take the position main scale reading. Main scale reading is the reading of the main scale with the zero of the vernier coincides. Then vernier coincidence, that is the division of the vernier scale, the nth division of the vernier scale which is exactly coinciding with any main scale division multiplied by least count. Total will give you the apparent position of the cross mark. Then sprinkle some lycopodium powder. Sprinkle some lycopodium powder on the cross mark so that you will not see the cross mark now. You will focus the lycopodium powder. That means sprinkling lycopodium powder means you are focusing the upper surface of the glass slab, which will give you this RT, lycopodium powder. You are focusing lycopodium powder means you are focusing the upper surface. You have focused this cross mark without slab means you have focused the lower surface. This is RT, this position is R1. So R3 minus R1 will give you real thickness of the slab. Okay. So now I am keeping it, you will focus. Again you have to raise it. So that this powder, lycopodium powder is focused. You can see the granules very clearly. Done. And again you will note down main scale reading as I have explained here. You will note down main scale reading plus vernier coincidence into least count. You will find the position R3. So this position you have written R3. This is without slab. This is R1. R3 minus R1 will give you real thickness, and in the lycopodium, when you have focused this, the cross mark appeared to be raised to some other point as here. Here, this point was raised to P1 with the slab. This is the apparent position. This position is R2, which you have observed with the microscope. This position is R3, this position is R2. R3 minus R2, this gives you apparent thickness. So this is apparent thickness, this is real thickness. Ratio, so R3 minus R1. R3 minus R1 will give you real thickness. R3 minus R2 will give you apparent thickness. Their ratio will give you refractive index. One observation over. Then you will start the second observation. For second observation, again you can bring it down. Anywhere you fix it and adjust this collimator screw. Remove this. Focus the cross mark again, adjusting this collimator screw. You move it upward, downward, and focus focus the cross map so that the intersection point of the cross map will coincide with the cross map cross wave inside. Done? So again you will find R1 and from here you will start observe R1, then put the glass map, you will focus again without disturbing the connector screw, you have to raise only this thing. So that you will get R2, then putting the lycopodium powder here, you have to raise it upward and take focus the powder only, that will be R3. And as I have done here, and refractiveness, 3 times you repeat. Take 3 observation, 3 times you find mu, that is refractive index. Then under calculation find the mean value of these 3 observations, which will give you refractive index of the material of the glass slab. And generally the refractive index of glass is around 1.5, so you are expected to get the result nearly equal to 1.5. It may not be 1.5 exactly, there may be some error in the experiment, it may vary from 1.45 to 1.55, that is also okay. Okay, thank you. Now sir will explain you the next experiment and I will come back again to show you the experiment.